Welcome to the Biology 182 lecture series on humans. This video is about how pollution affects the biogeochemical cycles. At the end of this video, students should be able to analyze the relationship between humans, pollution, and biogeochemical cycles. So what is a biogeochemical cycle? Well, bio means life, geo means earth, and obviously chemicals are chemicals. So a cycle is something that goes in a circle. It has a beginning and it continues up until a point where it returns to the beginning and starts again. The biogeochemical cycles are the way that the earth changes gases and chemicals and exchanges them between living and non-living things. There are 4 biogeochemical cycles that we will talk about today. The first is the carbon cycle. Carbon is the primary chemical of life. We are carbon-based. One of the main cycles that we use with carbon is the carbon dioxide cycle. Carbon dioxide goes through various stages and cycles around back to the origin. It can start with photosynthesis of autotrophs, where plants and grasses, trees, phytoplankton, and cyanobacteria can take in sunlight and carbon dioxide and use it to make sugars to sustain the plant. In doing so, it gives off oxygen. As well, organisms can eat the plants and gain the energy from the plants. Organisms, like animals, undergo respiration. This respiration, we can take in oxygen and give out carbon dioxide. This is one part of the cycle for plants and animals, taking up one of the gases and giving out the other. Another part of the cycle is ingestion. So organisms that eat plants or organisms that eat other organisms which eat plants will get all of the carbon and the sugars from the things that they're eating, but they also take in some of the CO2. The carbon and the CO2 being ingested is another way to be a part of this carbon cycle and how carbon is recycled throughout the earth. This is the biotic part, or the living part. As well, decomposition occurs. Decomposition occurs with detritivores, which are things that are fungi, earthworms, and bacteria that can break down molecules and organisms and put the components back into the earth. They can also release carbon dioxide and make carbon compounds. So when we look at this cycle, we have the photosynthesis, we have respiration, we have the intake of carbon and the excretion of carbon as well. So we're making and using carbon compounds constantly in the natural world. The carbon cycle has lots of aspects. The natural components of the carbon cycle that have negative impacts on the earth are things like volcanoes, forest fires, and hot springs. As volcanoes erupt or forest fires begin to burn naturally, these things emit CO2, and eventually an excess of CO2 can start to build. The natural version is in a harmonious balance with the plants and the trees photosynthesizing along with the phytoplankton or cyanobacteria. And this is helpful to keep the earth in balance. However, as humans deteriorate the atmosphere more and more to meet their needs, things like the burning of fossil fuels, deforestation to create additional room or for logging, or car emissions, these types of things add additional carbon to the atmosphere that isn't being in a regulated balance with the normal biotic and abiotic communities. This is creating a problem in the earth as these carbon or carbon dioxide emissions have nowhere to be broken down. One of the things I wanted to mention was how fossil fuels are made and why they're used. It takes fossil fuels millions of years to be created. They are a natural resource, but burning them is not natural. These fossil fuels are made of fossils, which makes sense, and the fossils are made of carbon. So the way we get coal is in a swampland. About 300 million years ago, there were lots of plants, and plants are made of carbon. These giant, enormous plants that died off in swamps could be buried. The dead plants are buried in dirt and sediment, and then water was over them. And some animals that lived in the water may have died and become part of that dirt. And the water keeps the dirt moist. And over time, there's enough pressure for the conversion of carbon into other things, in this case, coal. So under the rock and dirt layers, we can dig down and find coal, which was once dead plants. We're talking hundreds of millions of years it takes to make coal. Burning the fossil fuels adds that carbon back into the atmosphere. This is also how petroleum and natural gas are formed. In this case, it takes 300 to 400 million years of organisms living in the ocean dying and being buried over time with silt and sand, layering and layering and layering. Over time, as more water is on top, it takes another 50 to 100 million years to get enough pressure and heat to turn these plants and animal remains into oil and gas. Today, we have to drill down through all of that water, all of that sand, all of that silt to reach the oil and the gas deposits. This is 4 to 500 million years in the making. As well as adding the CO2 into the environment by burning coal and petroleum and natural gas, humans are also contributing to the lowered uptake of carbon dioxide and the lowered release of oxygen by using deforestation. They're cutting down trees and using the tree space for lands for cattle or other livestock. They're using it to build buildings and for infrastructure. And they're using it for logging the wood to make other textiles, buildings, all kinds of other things. So when we look at the global carbon cycle, we can see that natural things give off carbon and other things take up carbon, right? And so we have these pools of carbon and they go through these fluxes. So one of the things we want to remember is that matter, which carbon is, and energy cannot be created or destroyed, right? We're talking about the laws of thermodynamics and how matter and energy cannot be created or destroyed. They're only changed from one form to another. When looking at this, we need to remember that by burning carbon dioxide, it's changing forms. By burning carbon in plants and organisms and starting fires and giving out fossil fuel emissions, we are creating a change to what's already there into something else. Well, if we cannot change back to the things that the earth needed, now we have a deficiency. The crossing between one source to another is called the flux. So the blue numbers and descriptions are storage stocks of carbon, which is the total carbon amount stored on the earth. The earth's crust or the soil has around 100 million parts per gram. They call it a petagram. The oceans have almost 40,000 petagrams. Soil, as in topsoil, has around 1,500 petagrams, which is about 10 raised to the 15th. Okay. So when we look at these things, the red is the flux. And the flux is the movement between the stock, which is what we have in a pool, and what is being used. So it moves between the flux and the stock. It fluxes between them, right? And the carbon that we find most is, of course, in the crust or in the soils. But also there is a good portion in the oceans, just not nearly the amount as that is in the Earth's crust. Now you can see with fossil fuels, we only have 4,000 petagrams. And what that tells us is that when we burn through that, it takes millions, hundreds of millions of years to recreate these. So that is why it is a non-recyclable item. Burning carbon dioxide moves it into the atmosphere. Getting it back from the atmosphere is not easy to put it back into a carbon form unless we go back up and look at what things we can do to increase that usage of CO2 and the output of oxygen. We need more plants. We need things to be buried as they die. We need increase in shellfish and coral and phytoplankton. We need to be conscious of the food webs and not destroy our oceans or our earth. The ocean holds 50 times the amount of carbon dioxide as the atmosphere. And the ocean is called a carbon sink. The carbon sink soaks up CO2. It dissolves atmospheric CO2 at the surface. What happens in the water is that when we have organisms like phytoplankton, marine organisms or marine shells that die, they settle on the ocean floor and they will become part of the Earth's crust. Those organisms dying will be of benefit, provided that we still have marine life that can continue the cycle of putting out oxygen and using the carbon dioxide. Deep cold water currents bring our carbon back up and release it into the atmosphere. This is an important part of our carbon cycle. The sea has absorbed about a third of human carbon emissions, but it's becoming saturated. Saturated, like think about a hydrocarbon chain when it has those multiple bonds, right? If we have double or triple bonds in a hydrocarbon chain, we aren't going to have triple bonds. We'll have double bonds in a hydrocarbon chain. Then we see that it is unsaturated, right? But when we break those bonds and everything is single bonded, then we will have a saturated or fully immersed with hydrogen amount. Well, in the case of CO2, the saturation means the ocean can take up no more carbon dioxide. It has no more room for carbon dioxide. The carbon dioxide that's absorbed makes the ocean more acidic. This creates shell growth and shellfish or regular fish reproductive disorders, and it hurts shell growth. It also affects herbivores' health and development, and organisms that eat the fish and the shellfish. As well, the sea absorbs 80% of the Earth's heat. So as the planet gets warmer, the oceans continue to warm. The warmer they get, the less carbon they can hold. The currents will slow down. So now the stuff at the bottom isn't going to be released. It will also affect marine life and our ecosystems because we aren't getting that cycle of things continued. The next cycle we'll talk about is the water cycle. The water cycle is guided by precipitation and evaporation. You can see precipitation is the rainfall. Evaporation is the water being evaporated back into the atmosphere, or it is being taken back up by the atmosphere. It is then condensed back into a water form, turned into the clouds, and then eventually the clouds hold so much they are saturated and the rain comes down. So evaporation turns a liquid into a gas. We also have sublimation occurring, which happens when snow turns into a gas and is taken up into the atmosphere. As we have streams that form from the melting snow, And we have lakes and streams and freshwater storage areas that lead out into the oceans. This is known as surface runoff. This is another way for the water cycle to continue the evaporation precipitation portion of the cycle. Some of the water is given off as evaporation, some is surface runoff into the oceans or into freshwater storage. This cycle goes between water and the land and the plants that use water and the atmosphere and the organisms that use water. So plants not only take up water, they also give it off through a process called transpiration. And organisms do give off water as we sweat and while we speak in other ways, but also when organisms are no longer living and they become buried in the earth, they can also release the water that was in them. It will evaporate. So the water is a set amount. We can't create more water. We can only change its forms in the water cycle, which is why maintaining the amount of water we have is important. The sea level should naturally rise about 1 to 2 millimeters per year. Humans have decreased the amount of water runoff into the oceans by 0.8 millimeters per year, which is almost 1 millimeter a year. This is a major change. We are not getting enough water to continue our water cycle. The increase in relative humidity is having a huge effect on this as well. When we look at this diagram, we can see that R represents storage of water in reservoirs like dams or water towers or other stationary water conservation or reservoir areas. We can see G is the groundwater, where when you're mining, that groundwater underground can be found. I is for irrigation, the irrigation of plants, things with farms and with homes, people. We have U for urbanization, C for combustion, D for deforestation, and W for the wetlands. All of these things contribute to the water cycle, and they are ways that humans are processing things that affect that water cycle on the land, which creates less runoff into the oceans. So when we look at the human impact, we can see that we are increasing greenhouse gases, which is helping to contribute to acid rain, along with the toxicity of acidifying the ocean contributing to acid rain. We're increasing the Earth's temperatures, which is increasing the rate of evaporation. We are deteriorating ecosystems and even contaminating the drinking water by wasting all of this water and polluting it. We also increase antibiotic resistance through the pollution and through the disposal of antibiotics, which are then washed through the earth into the water cycle. We can see that the water cycle is a very important part of our world, but adding pesticides and fertilizers, road salts, pumping wells, mining, accidental spills, factory discharge, landfills, gas stations, sewers, septic tanks, solvents being put into our water systems, hazardous waste, all of this stuff leaks into our water, and eventually it will cause irreparable damage. The next cycle we'll look at is the phosphorus cycle. Phosphorus is naturally found in the soil on Earth. It is not naturally found in the atmosphere. It is also found in Earth rocks. So when the rain comes or it's really windy, the erosion of the rocks will contribute to phosphate. Phosphate is also found at the bottoms of lakes and oceans. It is part of the silt or sedimentary rock. When we have organisms that eat food and digest food and give out waste, we can see phosphates being exchanged. Decomposers break down organisms and plants, and they do create phosphates. The plants absorb the phosphates from the soil, and the decomposers decompose them and it leaches into our water. Then it becomes rock. And that is how we see the phosphorus cycle occurring. Well, all of a sudden, man makes fertilizers and detergents and industrial pollutants and sewage, and we have runoff from farming and ranching. And all of this is increasing the amount of phosphorus that we see in the world. So what is eutrophication? Eutrophication is definitely a toxic and poisonous aspect of our oceans. And what is happening is that the fertilizers that we're creating leaches into the water. When we have these excessive fertilizers and excess phosphorus in our waters, we start to create extra algae. The extra algae then blocks the sunlight from the other types of organisms that need the sun to photosynthesize. As the algae start to die and the photosynthetic bacteria or cyanobacteria or phytoplankton start to die, the oxygen levels in the ocean are lowered. Then the fish start to die off and they suffocate. We start to lose fish, we start to lose shellfish, we start to damage this ecosystem, irreparably damaging these ecosystems. It also poisons humans and animals. So anyone who drinks or plays in this water can be affected. It is toxic. It deoxygenates the ocean, so the fish die. This affects the fishing industry. So now people aren't being able to eat fish regularly or catch fish regularly. So the fishing industry is losing money, as well as people who rely on fish as part of their diet. They're losing that nutrient. It blocks photosynthesis, which affects our ecosystem as well as the marine ecosystem. And it affects recreation and tourism because we can't swim in those areas. It's toxic and poisonous. And it smells terrible. So no one would want to swim there anyway. The last cycle we'll talk about is the nitrogen cycle. The nitrogen cycle is a little bit complicated to remember. So you just want to make sure that you think about what is happening. We have nitrous oxide from fossil fuels that falls as nitric acid in the rainwater. Not so good, right? We see lightning that creates soil nitrates. Now we have nitric acid coming down and we have soil nitrates. The air is about 78% nitrogen gas. And then we have runoff from the nitrates in farming and ranching that also enter the water. This part of the cycle is a negative part of the cycle. The air with 78% nitrogen gas is part of the nitrogen cycle. This allows bacteria in the soil to fix the nitrogen from the air and put it into a form that is usable. It changes into nitrates. Plants absorb the nitrates. The animals eat the plants. The nitrogen compounds eventually break down into gas and return to the air after the organisms secrete or excrete the nitrogen. And decomposing bacteria break it down into other nitrogen compounds that are safe for the environment. When we look at this, we can see we have nitrogen fixation, then we have nitrification, assimilation, mineralization, and denitrification. This is how organic and dissolved nitrogen can be cycled back into the atmosphere and come back down. Well, as fertilizers are emitting this nitrogen into our water cycle, it is creating a problem with the number of bacteria that need to be able to fix the nitrogen so it can be used and put back into a usable form. You can see that the leaching of nitrogen is creating a mineralization and a mobilization of the nitrogen. It's getting stuck. And so the organic matter in the soil typically is soluble organic nitrogen, but sometimes it will have trouble being converted into a form that is usable on Earth. And that is where we're starting to have problems with the nitrogen cycle. So if we look at this, we have this atmospheric nitrogen, right? And these nitrogen fixing bacteria live near legume roots. And they then fix the bacteria into ammonification. And so they make ammonia, which then gets nitrificated, or nitrifying bacteria makes the nitrates. The nitrates then can either be assimilated into the plants taking them up as a food source, part of what they need, or it can be denitrified and put back into the atmosphere. These nitrates then that plants and animals take up can be put back into the earth as things die or are excreted. And the decomposers then, along with aerobic and anaerobic bacteria and fungi, will secrete the nitrogen back as ammonium, and it will continue in the nitrogen cycle. Assimilation uses the organic molecules and nitrogen compounds to create lots of biomolecules. Nitrogen fixing turns the atmospheric nitrogen into ammonia or ammonium. Nitrification converts that ammonia into the nitrate and nitrites. And then denitrification turns nitrates into the atmospheric oxygen. So that's the part of the cycle you want to focus on, how those things convert between one form and another. So how does the nitrogen cycle impact humans? Well, humans love to make fertilizers and burn fossil fuels and mine. They have lots of sewage waste, industry and trash landfill waste, as well as car emissions that are all giving off forms of nitrogen. Things like nitrous oxide are being released. Things like nitric oxide are being released. The removal of useful nitrogen is happening, as well as eutrophication. So what is happening is we're seeing an increase in eutrophication, acid rain, greenhouse gases, nitrous and nitric oxide, imbalances in our ecosystems, and contaminated drinking water. This is all in addition to soil infertility, which means we can't grow plants, so we can't have autotrophs that we need to make more oxygen for the atmosphere, as well as food. It's a part of the food web. It decreases the nutrients and it increases smog. So looking at these things more directly, nitrous oxide released into the atmosphere, it happens when fossil fuels are burned, right? It also happens when car emissions. That nitrous oxide is released through bacterial and livestock waste, as well as commercial fertilizers. And when it leaches into the soil, it leads to eutrophication of our oceans. When we remove nitrogen while mining, we are stealing that the nitrogen-rich mineral deposits that we need in the earth to be able to continue making biomolecules for life. When we have sewage being introduced into the soil, as well as waste, now we are having the ecosystem being disrupted around the land, and the biotic environment that uses that land or lives on that land is also affected, in addition to the aquatic ecosystems where we experience eutrophication. The Haber-Bosch process is artificial nitrogen fixation, and it's an industrial procedure that lets us make ammonia, and it is killing off the nitrogen in the earth that we need to continue the cycle. And it creates dead zones, like hypoxic areas that are usually found on the coast that have excess nutrients that fall into the ocean, right? And we're going to have detrimental effects on all the ocean ecosystems and everything around the habitats surrounding the oceans. The last thing I wanted to talk about is biomagnification, because as these pollutants increase, they amplify in organisms as they move through the food chain. So we'll have this pollution problem where the phytoplankton and bacteria and cyanobacteria are taking in pollutants. And as the zooplankton eat the polluted phytoplankton, now they have an increase in the chemical concentrations. As the zooplankton are eaten by the fish, they are getting more of those chemical concentrations. As the salmon eat the herring, more chemical concentrations. And as the orcas are eating the salmon. Now think about this. phytoplankton have very little amount in each of them. But if every zooplankton eats 5 phytoplankton, now they have 5 inside of them. If the herring eats 100 phytoplankton, it has 500 inside of it. So when a salmon eats 3, it's got 1,500 of these chemical concentration ingredients, right? So the whale eats 10 herring and we are in a world of trouble because as that whale now dies or is ingested by something else, we are releasing all of those pollutants. But all of these organisms, as they're increasing in the food chain, are getting a huge amplification the higher up they are. At the end of this video, students should be able to differentiate between biogeochemical cycles. They should be able to understand the impact of humans on biogeochemical cycles. They should be able to describe the sources of pollution that affect biogeochemical cycles.